Imagine you're trying to connect a series of dots that clearly form a wave-like pattern, but all you have is a straight ruler. No matter how you angle it, your straight line will always be a poor representation of that curve. This is the essence of underfitting in machine learning. It is what happens when your model is just too simple to understand the complex patterns hidden within your data. It's like sending a first grader to solve a calculus problem. The tools are just not sophisticated enough for the task at hand. An underfit model is a recipe for disappointment. Picture a state-of-the-art robot designed to sort different types of fruit, but it keeps putting oranges in the apple bin. This poor performance is a direct symptom of underfitting. The model hasn't learned the fundamental differences between the fruits, so its predictions are consistently wrong. This isn't just a problem during training. It's a critical failure when the model faces new, unseen data. It fails to generalize, meaning it can't apply what it learned to real-world situations, rendering its predictions unreliable and essentially useless. So, why does this happen? There are a few core reasons. First, the model itself might be too simple, like using a basic linear model when a more complex neural network is needed. It's like trying to assemble a sophisticated engine with only a hammer and a screwdriver. You lack the specialized tools required for the intricate job. Another major cause is insufficient training. Imagine a training progress bar that abruptly stops at 20%. The model simply hasn't had enough time or seen enough examples to learn the underlying patterns, leaving its education incomplete. Finally, over-regularization can be the culprit. Think of a dial labeled simplicity that has been turned all the way up. Regularization is a technique to prevent a model from becoming too complex, but when applied too aggressively, it constrains the model so much that it can't learn anything meaningful. Thankfully, underfitting is not a permanent dead end. There are clear, effective strategies to fix it. The most direct solution is to increase the model's complexity. Visually, this is like transforming that initial, ill-fitting straight line into a more flexible curve that perfectly traces the data points. You might switch from a simple model to a more powerful one, or add more layers and neurons to your neural network. Another powerful technique is feature engineering. This is the art of transforming your raw data into more meaningful inputs for your model. Imagine, instead of just feeding the model images of apples, you provide it with features like color, shape, and size. It's like turning raw ingredients into refined components, apple pie and apple juice, that are much easier for the model to understand and work with. Lastly, you can tune your regularization. Simply turn down that simplicity dial, giving your model more freedom and flexibility to capture the true complexity of the data. Ultimately, the goal in machine learning is to strike a delicate balance. On one side of a scale, you have underfitting, where the model is too simple. On the other, you have its equally problematic twin, overfitting, where the model is too complex and memorizes the training data instead of learning from it. The sweet spot lies in the middle, a well-fitted model that accurately captures the underlying trends and generalizes effectively to new data. Achieving this balance is the key to building powerful models that can make accurate predictions and solve real-world problems, turning data into genuine insight.